Hello, in this video I'd like to finish my decomposition of the regular functions. In previous videos I've shown that any causal length preserving regular function can be written as a multivariable composition, a cascaded composition, of characterwise functions and truncated run maps for very specific automata, specifically permutation automata and the 1-bit memory automaton. But what about regular functions that aren't causal, or regular functions that aren't length preserving? Let's start by looking at the regular functions that aren't causal. Remember that a regular function is defined as a function where there's a corresponding finite state automaton that reads in an input-output pair and tells you if this is the correct output for this input. And of course, it being a function, there has to be only one output for each input. When we were looking at causal regular functions, each character of the output was determined by only the previous characters of the input. Future characters of the input had no effect on it. And we found that the corresponding automata effectively only looked at the input when determining how they behaved. But with non-causal functions, things are a little bit trickier. In order to figure out whether this C is the correct character in this position of the output, we might have to look at both past and future characters of the input. Of course, since the output is determined by the input, we don't really need to look at other characters of the output. Let me show you an example of a non-causal regular function. So let's take a look at the function that takes in a word that consists of A's and B's and outputs a word consisting of C's, D's, and E's, and all B's become D's. So that's straightforward. And then if we see a group of A's in a row, so for instance it could be surrounded by either an end of a word or B's on either end, then it becomes an equal length configuration that looks like this, with D's on either end and an alternating pattern CE, CE, CE that ends with a C. This is a bit of a complicated function, but I've deliberately added in two non-causal features in order to show off how we can deal with them. The first non-causal feature is this D at the end. We have to know when we're reading in an A that it's the last A of a particular run of A's in a row in order to turn it into a D. And then also when we're looking at the second A in our sequence of A's, we have to decide whether to turn that into a C or an E. And in order to know that, we need to know whether this distance here, whether the run of A's that we're looking at is even or odd. This is of course a length preserving function, and I claim that it's also regular. Let me show you the finite state automaton that accepts it. This automaton also has a failure state, which if we are in a particular state and we read some sort of character that doesn't have an out arrow, so for instance, if we're in state 1, there's no out arrow labeled BC. Which means if we're in state 1 and we read a BC, we go to the failure state and we stay in the failure state and we never accept. I've avoided drawing the failure state for simplicity, but this is the same sort of construction we've been doing all this time. Notice that unlike the automata for causal regular functions, if we're in a particular state, the input does not determine where we go next. If we're in state 1 and we read an A, then we could read lots of different output characters, and the output character, there's only going to be one output character that takes us ultimately to an accept state for this word. Remember that this is still a function. Every input gives us exactly one output. But determining which of these output characters is going to take us to an accept state when we're done reading the word depends on how many A's in a row there are. We need to know that information in order to determine what output character comes next in an accepting run. Now I want you to imagine a situation where we're given the input and we want to determine what sequence of output characters will give us an accepting run. This situation is very similar to a non-deterministic automaton. right? We could imagine we're in state 1, we read an A as an input, then we could wind up in any of these 3 states here. And so this process of taking our inputs and determining what the correct sequence of outputs is that will get everything accepted by our automaton is similar to finding runs for non-deterministic automata. But remember, we know how to do that. There's a power set construction that not only allows us to determine if there's an accepting run of our automaton, but also to, by working forwards through the power set construction and then working backwards, reading the states that we got through our power set construction to produce an accepting run. And that's kind of what we're doing in this situation. Let's suppose that we have a word that looks like this. Let's work through this word character by character, keeping track of the different output characters of the input that we could be reading alongside it, along with the states that those output characters would take us into. For instance, we start off in state 0, and then we'll read an A. Well, what are the possible things that we could do upon reading an A? Well, we could read an AC, and that would take us to the failure state. And I'm actually going to completely ignore the failure states. You could keep track of them in this construction, but there's no reason to do so. But we could see an AD, and that would take us to state 1. And so I'm going to write this here as D1. We could read an AD, and it would take us to state 1. It's worth noting that this construction that I'm doing right now is not strictly causal, it's causal. This character here is influencing what I'm going to write below it, which is slightly different than what we've been doing all this time, but remember that every causal function can be written as a composition, a cascaded composition of a characterwise function and a strictly causal function. Now suppose that we're in state 1 and we read another A. What could happen? Well, there's actually 3 possibilities. We could read a C and wind up in state 2. We could read a D and wind up in state 4. Or we could read an E and wind up in state 3. And I'm going to keep track of this information like this, and I'm actually going to draw in some arrows. Now, suppose that we're in state 2 and we read an A. Well, if we read an AC, that will take us to the failure state. There's no edge coming out of state 2 that's labeled AC. On the other hand, we could read a D and that would take us to state 4, or we could read an E and that would take us to state 3. If we're in state 4 and we read an A, there's actually no edges coming out of state 4 that have an A in them. So this is a dead end. If we're in state 3 and we read an A, it has to be an AC, and that'll take us to state 2. So I'm using these arrows here to keep track of possible paths that we could be taking. It's worth noting that at this point and at this point, the set of states that we have access to and the characters that we could have read to get us there are actually the same. These two are, in some sense, they're the same state. We're in the same situation, so we don't actually need to bother making a distinction between these two. Remember that we're doing a power set construction, so the order of the elements of that set don't really matter. It's just that it's easier to draw these arrows this way. Again, if we're in these states and we read an A, what could wind up happening? Well, in state 4, nothing. In state 3, we can go to state 2 by reading an AC. And in state 2, we could go to state 4 by reading a D, or state 3 by reading an E. Next, we read a B. Well, if we're in state 2 and we read a B, we're sunk. If we're in state 4 and we read a B, it has to be accompanied by a D, and that'll take us to state 0. And if we're in state 3 and we read a B, we're also sunk. And we continue this construction for the rest of the word. So just like with the power set construction, we're going to want to find a path through this tree that represents an accepting run of our automaton. Except this time, we're getting information about not only the run, the sequence of states that we were in, but also the output characters that we would have to read in order to have that accepting sequence of states. And in order for this sequence of states to be an accepting run, it has to end with an accept state. After reading this last A, we have access to states 4, 3, and 2, but only 4 is an accept state. So we're going to wind up here. And what we're going to want to do is work our way backwards through this construction here in order to figure out the accepting run and the accepted output. This state 4 could only happen if we were in state 2 before it. This state 2 could only happen if we were in state 3 before it. And so on and so forth. And so here we have the accepting run. So what does this mean in terms of regular functions? Well, we could formalize this tree construction as the run of a very specific automaton. The states of the automaton are collections of output characters and states that we could be in. And if we read a particular character, we have to ask if we're in a particular state and we read that character, what states could we go into? And we do that for every single state. And because there's only a finite number of configurations that we could have at any one step, and the way to go from one configuration to the next, depending on what character we read, is well defined, we have the run of a finite state automaton. Although this is not the truncated run, this is the run with the first character removed. So the function from input words to this diagram we got without the circles is actually a causal regular function. And then the process of working backwards through this diagram and outputting the sequence that got us to an accept state is a reverse causal regular function of this sequence of states here. And then from here we can apply a characterwise map of simply ignoring the states to get the appropriate output for this input. In other words, we were able to write this regular function here going from this input to this output as a cascaded composition of a causal regular function and a reverse causal regular function. I like to call this reverse causal regular function a harvester because it's somehow taking all of this data that's been accumulated by the determinization automaton and harvesting from that data the accepting run. So every regular length preserving function can be written as a composition of a causal length preserving function and a reverse causal length preserving function. And we've seen before that causal length preserving functions can be written as cascaded compositions of characterwise functions and truncated run maps for permutation automata and the 1-bit memory automaton. And similarly, we can write any reverse causal length preserving function as a cascaded composition of characterwise maps and reverse truncated run maps for permutation automata and the 1-bit memory automaton. What about if we have a regular function that isn't length preserving? Let's start off by remembering what it means to have a regular function that isn't length preserving. Remember that we've assigned a special character, the octothorpe, as a special end-of-word character that can only appear at the end of words and is used to pad the inputs to an automaton so that they're all the same length. If we wanted to express a function where f of BA is equal to ABBA we would need to have a corresponding automaton that accepted the input that looks like this. We would need to pad out our BA input with a bunch of octothorpes so that it was the same length as this other input, and then we could feed it into our automaton. But here's the thing. Every character of the output past the end of the input word has to correspond to a new state of the automaton. Suppose that the same state showed up twice. Let's say that state Q1 shows up between these two characters here. So after reading this B octothorpe, but before reading this A octothorpe, we're in state Q1. And then suppose that at this point here, we're also in state Q1 after reading this A octothorpe. Then what this means is that we found a loop in the automaton diagram going from state Q1 back to state Q1. And we can follow this loop as many or as few times as we want, and it's not going to affect the overall operation of the automaton. For instance, we could remove this chunk entirely, and we would still, after reading this bit, get to state Q1, and just before reading this bit, we would be in state Q1, so after we read this character, we would wind up in an accept state. And so this would also be an accepted input of our automaton. In other words, f of BA would be both ABBA, BAB, and ABBB. And lots more things besides. We could also double this segment. And so this automaton can't correspond to a function. So if we have a regular function, like we claimed this thing was supposed to be, it can't be the case that the same state shows up twice within this past the end of the input, but we're still doing output stuffs, part of the input to the automaton. This gives us a very important fact. Suppose that we have a regular function. Then there's going to be some n, and that n is going to depend on the function. Different functions are going to have different n's, such that for any word, the length of f of w is at most the length of w plus n. So we can have regular functions that, for instance, add an a onto the end of the word, or add 5 a's onto the end of a word, or round up the number of a's on the end of the word to the nearest multiple of 7. But all of these functions have some sort of strict upper bound on the number of new characters they can add to the length of a word. I'm going to take advantage of this fact here by writing our function f as a composition of functions that perform the following operations to a word. Suppose we start off with some word. The first transformation that I'm going to want to apply to this word is to tack on a bunch of fake end-of-word characters to it. Specifically, n fake end-of-word characters. I'm going to use an asterisk for the fake end-of-word characters. And so I'm going to apply the successor asterisk function, the function that tacks an asterisk onto the end of a word, composed with itself n times. So really this is we can just toss in successor asterisk into our generating set, and by composing it with itself n times, we can apply this operation. N is determined by the function f, so when we're doing this decomposition for a specific function f, we just have to ask what is the n for that particular f, and then apply the successor asterisk function to itself n times for that specific n. This produces a word. We then will apply a length-preserving modification of our original function f. Suppose that f of AB is ABB, then our modified version of f, it's going to have to be length-preserving, so we're going to want a 4-character output, and we'll just have ABB, the output of f, with another fake end-of-word character tacked on to the end. The key thing here is that because we've tacked on n asterisks, where n is the lengthening factor for the function, the maximum number of characters that we can increase the length of a word by, we don't have to worry about f of this input here exceeding the space that we've given it. we have an extra 2 characters. In this case, we didn't use both of those extra 2 characters, but because we have them there, we don't have to worry about this input giving us an output that's too long. We can always fit it into the space provided and then add asterisks at the end if necessary. And then finally, we will apply a function to remove all of the fake end of word characters from this word here. I'm going to call this function unpad. The process of showing that this length-preserving modification of our original regular function is itself regular is a little bit tricky. One has to add on the ability for your original automaton to accept pairs that look like asterisk asterisk. But perhaps the trickiest thing about this construction is what happens if we apply this function here to AB. Remember that this function here should agree with our original function and is also length preserving. Well, there's a problem. Our original function thinks that f of AB is ABB. So there's not really anything this modified function can do if it doesn't have enough characters to output the appropriate output ABB. Fortunately, in practice, when we're using this new function in the compositions that we're actually going to use it in, we don't have to worry about this case happening. We're always going to pad with an appropriate number of characters so that there'll always definitely be enough room to put the appropriate output, potentially with some extra padding added on. That is to say, in practice, our modified version of f is never actually going to read in AB. But we still need it to return something when we feed in AB, because it has to be a function. In order for all of the previous work that we've done about decomposing length-preserving regular functions to apply, not only does this thing have to be length-preserving, but it also has to be a function. Fortunately, we can just say, if the input is too short to be able to do this sort of construction correctly, just return the empty word. I don't know. We can return anything. It doesn't matter what this function returns because we're never actually using this particular value of the function. We're only ever going to use this function with appropriately long inputs in practice. Fortunately, we can do this. Remember that if we construct a function piecewise, where each piece is regular and the function on each piece is a regular function, the resulting piecewise construction gives us another regular function. And so if we have a function that applies this modified version of f, in the cases where we can do that, where we have enough room to do that, and if we don't have enough room, returns, I don't know, the empty word, this is still a regular function. And so our final decomposition of a general regular function looks like this. We can break down any regular function as a composition of copies of a specific successor function, the unpad function, which removes that character from the end of a word. It seems a little bit weird to have a special character like this, because we can just use characterwise functions to change which character we're tacking onto the end or which character we're removing from the end of a word. But this is all we need, and this is really all that we're going to use. And then finally, a length-preserving regular function. Earlier in this video, we saw that length-preserving regular functions can be written as compositions of causal length-preserving regular functions and reverse causal length-preserving regular functions. These causal length-preserving regular functions can be broken down into characterwise maps and strictly causal length-preserving regular functions, which can then in turn be broken down into characterwise maps and run maps on permutation automata and the 1-bit memory automaton. And similarly, we can break down reverse causal length-preserving regular functions into characterwise maps and reverse truncated run maps for permutation automata and reverse truncated run maps for 1-bit memory automata. And so here we have our complete generating set for the regular functions. Some sort of successor operation, some sort of unpadding operation, characterwise maps to glue everything together, and then truncated run maps for permutation automata, 1-bit automata, and reverse truncated run maps for permutation automata and 1-bit automata. At this point, I hope to shift my attention back to the non-standard models of weak S1S. Technically speaking, some of the decompositions that we've done here won't really be necessary for our analysis, but it will be useful to have these in mind. Remember that our non-standard models of weak S1S are going to have to be closed under the functions that we can describe in that logic. After all, they're closed under these functions in the standard model, and we can express that they're closed under these functions in the logic, and so therefore all the non-standard models are also going to have to be closed under these regular functions. We're going to have to be able to make sense of running an automaton on a non-standard length input. So thanks for watching. Let me know if you have any questions in the comments below, and I hope to see you in a future video.